These are sound waves in slow motion, moving through air. As the wall vibrates back and forth, the air is alternately compressed and expanded.
Oh, yeah.
Blue bands show the compressed regions. Through air at room temperature and sea level pressure, sound travels about 340 meters per second or 740 miles per hour. This distance is called a wavelength. The frequency of the wave is the number of bands passing a point every second. Wavelength times frequency is the distance the wave travels in 1 second, or wave velocity. All frequencies, or wavelengths, travel with the same velocity, but the frequency determines the wavelength.
You would see sprocket holes if it, well, you do see a little bit of them if it was totally off.
Yeah, that's part of it.
Yeah.
Higher frequencies have shorter wavelengths. Of course, we're very much aware of sound waves through our sense of hearing. This sound, picked up by the microphone, has a frequency of 440 vibrations, or cycles per second, and a wavelength of 78 centimeters. We've altered time and distance scales to make the waves easier to see. This wave has lower frequency, longer wavelength, and lower pitch. Our ears can normally hear frequencies from 20 to 20,000 cycles per second. When the source moves toward us, we hear a higher pitch, and as it moves away, a lower one. Radial motion changes pitch, but transverse motion doesn't. This phenomenon is called the Doppler effect. Let's compare these sound waves with electromagnetic waves moving along the x-axis. We need 3 dimensions to show an electromagnetic wave. The wave is made up of an electric field, shown with yellow lines, and a magnetic field, green lines. Here's one wavelength. At a point, the fields oscillate with the frequency of the wave. Here's a longer wavelength and lower frequency. The human eye is sensitive to the spectrum of wavelengths from 4,000 to 7,000 angstroms. Radio waves have much longer wavelengths and X-rays much shorter. Electromagnetic waves also behave according to the Doppler effect. Astronomers use the effect as a tool to measure the radial velocity of stars. This is the constellation of Virgo. If we pass light from this star through a spectroscope and look in the blue region of the spectrum, we see an absorption line due to atoms of calcium in the atmosphere of the star. We know that calcium absorbs light at this wavelength. Because of the Doppler effect, starlight shifts to longer wavelengths. The star is moving away from us at 30 kilometers per second. Another star shows a Doppler shift to shorter wavelengths. It has a velocity toward us of 12 kilometers per second. Let's watch as the Earth goes around the Sun. A year goes by in 6 seconds. The orbital speed of the Earth is 30 kilometers per second, And we see a changing Doppler shift as the Earth moves toward and away from these stars. Astronomers must correct their observations to take Earth motion into account. The radial velocities of about 15,000 stars have been measured by means of the Doppler effect. This effect is one of our major tools for exploring the universe.